Firstly, let me just thank the organizers for the invitation to speak here. I really love the KITP workshops and regret that I wasn't able to attend, but unfortunately, the government shutdown prevented me from traveling. Oh, my slides are not advancing. What's going on there? Okay. So today I'm going to tell you about two different directions in my group. One is a new set of techniques that we've been developing for creating low entropy Hubbard systems with applications to dynamics, but also ground state systems. And then in the second part, I will do a sort of a hard turn and discuss how in the group we use many body dynamics for engineering certain kinds of quantum states that improve the performance of quantum sensors, and in this case, optical atomic clocks. Okay, so diving into this first part, this falls broadly into the area of many body systems of neutral atoms, for which there's a sort of a well-known important challenge here, which is figuring out how to combine scalability, that is preparing large ensembles of these systems, and furthermore, combining that with microscopic control and detection, that is the ability to individually detect and manipulate qubits or atoms or particles, what have you, in these systems. Within neutral atoms, there have been two platforms that have been quite powerful in this regard. One is quantum gas microscopes, where a microscope is used to individually resolve atoms in a standing wave of light, an optical lattice. And importantly, the atoms that live in this optical lattice display much of the physics that we believe occurs in solids with electrons hopping in crystals. And so what this allows you to do is to resolve single atom resolve many body snapshots of itinerant many body systems. On the flip side, there's another suite of experiments that I think already were presented at this conference based on optical tweezer arrays. Importantly, in these experiments, one benefits from being able to arbitrarily project different kinds of tweezer arrays, for instance, allowing you to study things like quantum magnetism and frustrated spin systems. But typically, although not all the time, the atoms are pinned in space. These are not itinerant models. They more often are programmable spin models. And so the question that we've been thinking about is whether you can combine the control that you have in these tweezer array systems with the kind of physics that one typically observes in these quantum gas microscope systems. That is, can we combine programmability with itinerant models, studies of itinerant models? Okay, so there have been a number of different approaches to this problem, some in quantum gas microscopes and others in tweezer systems. The approach that we take is really this brute force approach, where we combine an optical lattice potential that's registered with an array of tweezers. And so this allows us to get at using tweezers for really controlling individual atoms within a Hubbard system that lives within this lattice. In the second part of my talk, we actually use this same platform. And the point there is that the fact that we have many sites on which we can cool the atoms, detect the atoms, and actually perform rotations on something called the clock transition in these atoms gives us a much more scalable system. But as I mentioned, the fact that we have these tweezers combined with this lattice and they can resolve individual sites of this lattice means that you retain the control that you have in these tweezer systems. And one other detail here is that my group really has focused on the use of alkaline earth atoms, and in particular, what I'll be talking about right now is work with strontium-88. The importance of which will become clearer as I move along here. Okay, so in this new platform, a typical sequence looks as follows. Sorry, I just want to have my out here so I can keep track of time. So we load an array of atoms and implant them into the lattice. So we load the tweezer arrays in a stochastic fashion, implant them into the lattice, which makes an image like this. We can then use the tweezers to rearrange the atoms in this lattice and then actually cool the atoms. We can do this in nearly arbitrary configurations. So this is an array of doublets on nearest neighbor sites. This is an array of atoms arranged on every other site of the underlying optical lattice. This is strontium-88 pointing at a strontium-88 atom, and this is just rearranging a lot of atoms. And maybe one of the key things I'll emphasize here is that, to my knowledge, these are the smallest length scales on which people have done atomic rearrangement. And that was one of the key challenges for really making this all work, figuring out how to get that to perform at high fidelity. Okay, so with that, we have removed entropy in the system associated with the spatial configurations of the density of the atoms. But the atoms are are living in harmonic oscillators at individual sites of this lattice, and so we actually need to also cool them in their mechanical degrees of freedom. And for this, we do something known as resolved sideband cooling. The key point is that strontium has a narrow line transition that's particularly good for this kind of laser cooling. I won't go into the details, but I'll just say that the point is that if you have a narrow line with transition, the motional occupation that you can end up with using this kind of cooling technique goes as the square of the ratio of this line width to the trap frequency on the site. So for the experts, this is a sideband spectra showing the kind of temperatures that we can get, and the numbers here basically correspond to, typically we can be above 95% in 3D, and when we really push, greater than 98%. Okay, so that takes care of both the density and now also the motion. Once we've done that, we can let the atoms go in this underlying lattice potential, having now initialized the many-body state that we want to work with. So just as a warm-up, the way this looks for a single particle, if we implant an atom in this lattice, we expect that it's going to tunnel in it. Oh, whoops, something didn't show up on my graphics here. And so in this video here, we implant an atom in the center here where this circle is. And then we run the experiment many, many times, and this blue smudge is where the atom ends up. And then we see an interference pattern associated with the 2D quantum walk of this particle. So trivial physics, but a nice sort of check that we're doing what we expect, which is good. The next thing that we can do is address the question of how much is this system looking bosonic? In other words, are we really preparing indistinguishable particles in the lattice? The way we do this is by preparing the two atoms on neighboring sites, and then allowing the atoms to tunnel in time for about a tunneling time. What this does, in particular, is it results in something known as Hong-Mandel interference. In particular, we can ask the question, if the atoms start on these two sites here, what is the likelihood that they end up in that same configuration after this tunneling time of 1 millisecond? And importantly, what one finds is that the two particle quantum amplitudes for both particles to tunnel and for both particles to stay where they started coherently cancel. So you're left with just the atoms always appearing on the same sites. And so this is formally identical to this idea of the Hong-Mandel dip that was observed in photonics. So for photonics folks, that's sort of what we're doing here. For the many-body theorists in the room, this is sort of like a swap test that we're doing. So we can do that with the atoms and quantify that we have indistinguishable particles. That's really a measure of the overlap of the two density matrices of about 99.5%. I'll add that one thing that we do here is have a small bit of post-selection at the few percent level due to the fact that sometimes the atoms are motionally excited in the 2D degree of freedom, and those atoms end up in a higher band and are lost. Okay, so the first thing that we did with this was an experiment with many particles, but the isotope that we're working with is actually one which lacks interactions. It's largely a non-interacting atom, sort of like a photon. And so the physics that we look at is as follows. So we ask the question, suppose you start with some initial configuration that looks like this, and we want to know what's the likelihood that it ends up in some final configuration that looks like this. So there are multiple different many particle paths that contribute to that outcome. And sorry, in addition, this system is described by a single particle unitary UJK, which just describes the quantum amplitude for a particle starting on site J to end up at site K. So the quantum, to answer this question of the probability to end up in this configuration down here, you have to multiply all of these different quantum amplitudes for these single particle paths. But of course, there are multiple different many particle paths, all of which coherently add up, that give rise to this final output probability. And it turns out that computing this probability is equivalent to computing the permanent of a matrix. Probably some in the room are recognizing this as essentially the boson sampling problem. This idea and the hardness of computing the permanent has motivated a number of experiments in photonics. This is a picture from Joaquin's group where they made this gargantuan interferometer for doing these kinds of experiments. And at least the state of the art last year, I tried to look this morning and I didn't see any updates on this, was about for Fock states, the initial states here, 14 photons on 60 modes, and for squeeze states, 100 photons on a couple hundred modes. The original paper by Aronson and Arkhipov really focused on Fock states. There have been other papers that point out that you have a hardness criterion for squeeze states as well, but there's a lot that you need to fulfill in order to make that work, and you're much more sensitive to loss. So doing this with Fock states is nice. So the first thing that we did here is we started with 3 particles. And you can immediately see that there's this spikiness in the distribution, both for distinguishable particles, which we can simulate in the experiment. I can explain that if there are questions about this, but for now, I'll just say that we can do it. There's this spikiness in the interference pattern, which becomes a bit more spiky in the indistinguishable case. And this spikiness is really what you're trying to calculate. Sorry, I should have said the x-axis here is just an index telling you the different possible configurations in the output modes. This is for particles on separate sites. Sometimes we get 2 particles on the same site, and sometimes we get 3 particles on the same site, which the enhanced probabilities for the indistinguishable case relative to the distinguishable case for these 2 examples here is the hallmark of bunching that you expect for indistinguishable bosons. Okay, but one thing that you can see here is that while this spikiness seems like something that you can measure and compare to theory, that's the gray, the probability for each of these outcomes is getting smaller and smaller as the size of your instance gets larger and larger. So one really wants to have some sort of more efficient way of quantifying what you're doing. And so one of the things that you can look at is just bunching in general. So we look at the probability that all of the particles end up in the same output mode. You can see here in red, and a dark red is what the theory for the line is the theory, the points are our data. In pink is what you have for distinguishable particles. So you can see this is a very sensitive measure. And in fact, for if you just have 1 particle distinguishable from all the rest, this is what you expect in the dashed line here. So this is a sensitive measure, but once again, one sees that the probability of these events is getting smaller and smaller as your atom number increases. So that's problematic if you want this to be an efficient metric. So instead, what we did in this experiment was inspired by this paper from Valery Skesnovich from 2016. And what they show in this paper is that if you actually just consider any random partition on the lattice, so for instance, this random set of sites shown in red, and ask the question, what is the likelihood that all of the particles end up in that random partition? Then that is a quantity which is actually maximized for bosons, and therefore serves as a quantifier of how bosonic or indistinguishable the atoms are. And so we use that. This was a set of ideas that were put forward by my student, Aaron Young, and Sean Geller, who's now a staff scientist at NIST. And we were collaborating with Manny Knill and Scott Glancy on this work. But what you see here on the y-axis is that this probability for this generalized bunching, which is what we refer to it, grows as the number of particles increases. The circles are our data. These lines here correspond to a theoretical simulation of the experiment, adding more and more distinguishability associated with the finite temperature of the atoms in the direction transverse to the lattice. And you can see that this solid blue line is pretty close to the data that we actually measure, while if we do control experiments with distinguishable particles, it's also consistent with what we'd expect for basically an infinite temperature system. So this is a nice check that this quantifier at least is sensitive to the kinds of things that we're thinking about here. Okay, so, and this is how it looks when we actually run the experiment. So we rearrange 180 atoms here, and then we let them go and sample from that distribution. That was the largest instance that we went to here. And this is where the system sizes on which we could actually do the simulations using this Clifford and Clifford algorithm. Okay, so before I move on to the second part of the talk, I just wanted to highlight some things we're working on now, but they're not sort of either the topic of this workshop or complete stories yet. So one thing is we switched isotopes and we can work with very strongly interacting systems. And so just to illustrate how this modifies the transport dynamics, we rearrange a system like this for strontium-88, which is not interacting. The average density distribution looks like this, whereas for strontium-86, where you have these strong interactions, the particles are somewhat confined within the center, and you get this much smaller distribution in the dynamics. Another thing that we've been doing, which we're just about to post, is preparing ground states with the system. So we came up with a protocol where we start with a disordered array, and then by doing a bunch of gymnastics controlling the atoms, we can end up with distributions that seem consistent with preparing superfluids on the lattice, but just starting from, again, individual atoms that are ground state cooled as opposed to, for instance, a degenerate Bose gas. Just as an outlook on this section, I want to highlight some perspectives on this. So one is that relative to a typical quantum gas experiment, the cycle times for these experiments can be very high, which means that if you have observables like entanglement entropy, which require lots of statistics, this might be a very good system for resolving such quantities. And furthermore, the control that we have, so for instance, we can apply walls on top of the lattice very easily, which can also be done in quantum gas microscopes too, could allow you to use some new ideas from Soon-Won Choi for measuring nearly arbitrary observables in these systems. Another direction of interest to us is there have been these really beautiful experiments from the Greiner group preparing low entropy Fermi Hubbard systems. And those typically start from a distribution that looks like a gapped product state of Fock states on the lattice, which is exactly the kind of many-body state that we can initialize as well. So one might imagine using this kind of approach in the context of these techniques that I was just describing. Another direction of interest that I think now a couple of groups are considering, so there's been this challenge in the community to prepare low entropy ultra cold molecules with some very exciting progress over the past several years, in particular from Sebastian Will's group, Juni's group, and Wasim Bakr's group. The key challenge here is that the evaporative cooling that one typically performs can be limited by the inelastic collisions that occur between the molecules, which is something that you can avoid using these kinds of assembly, these like bottom-up assembly techniques that I just described. Finally, one sort of further in the future idea that we've been thinking about is whether this hybrid architecture might be useful for producing fermionic quantum circuits. And this is something that this is published this year, that we worked on with Hannes Pichler and also Peter Zoller. And in particular, in this paper here, we showed this idea of how you might be able to do error correction in such a system, which benefits from using this hybrid architecture. Okay, so now I'm going to move on to the second part of my talk. I'm running a little bit behind, but I think I'll be all right. So the second part, as I mentioned, is on a completely different set of physics, and in particular, looking at the idea of quantum sensing. So this is the idea that you might have some quantum state. It could be a many-body quantum state that's an ensemble of qubits. These qubits evolve under some Hamiltonian H, which might be proportional or is likely proportional to some parameter of interest that you're trying to measure in a quantum sensing context. So for instance, if you had a magnetometer, the Hamiltonian that you evolve with might be proportional to the magnetic field in the lab, or would be proportional to the magnetic field in the lab. And therefore, this overall unitary here just realizes a rotation of this quantum state about the z-axis with an angle that depends on this parameter that you're trying to sense. After you allow the system to evolve, you then perform some measurement, which in general could be in an entangled basis, but what you measure in the end are just classical bit strings. And so the goal of quantum sensing is to figure out what are the optimal input states to infer the parameter that we're trying to measure or quantify based on these bit string outcomes that we detect in the end. And importantly, it turns out that there are certain entangled states that can actually improve the performance of this overall protocol. So the sensor that we work with is an optical atomic clock. Just in brief, this is the idea that you have a laser which serves as your local oscillator. Not all lasers are perfectly stable, of course. You can stabilize them against optical cavities, but not all optical cavities are the same, and there's susceptible environmental perturbations. And therefore, you compare the frequency of the laser to the frequency of an atomic transition, which serves as an absolute reference. And the performance with which you can do this is typically quantified by this thing known as the stability, which tells you your precision as a function of averaging time tau. And so, for one, this depends on the length of time over which you can do a coherent phase comparison between the lasers and the atoms. So that means you need to make better and better lasers. There's been Herculean efforts in this regard, notably at JILA and Juni's group, and also at PTB, where they've created lasers that have line widths of less than 10 millihertz. You also care about the atoms, and in particular, having a high frequency oscillator, and in particular, uh, uh, the leading clocks these days are based on optical transitions. And this is important because it really sets the density of ticks on your ruler of time, basically how many revolutions occur on your clock in 1 second. So you care about the frequency of the transition, and you also care about having many atoms because of the quantum projection noise that arises when you do these bit string measurements at the end. Okay. This performance here is known as the standard quantum limit. This just means it's the limit on the performance of starting with an initial product state or non-entangled state for the atoms. So my group has developed over the past several years this platform of a tweezer-based clock. This was something growing out of a collaboration at JILA with the E group. We were able to show coherence times of about 20 seconds in this system. This was the first time in 2020 that such coherence times have been observed. They've now been extended in a number of other systems. We've also been able to see single particle coherence times of 48 seconds. This is really emphasizing that this is a powerful platform for doing optical atomic clocks, and we can get pretty respectable stabilities and precisions in these systems. Okay, but the focus of this part of the talk is really about, need a sip of coffee there, entangled clocks. And so let me walk through the different kinds of states that one can produce for improving the precision of a clock based on entangled states. So one very well-known state is a squeeze state. This is a state which has reduced variance along one quadrature at the expense of increasing it along another. If you're measuring rotations about the z-axis, then you can rotate this distribution so that this reduced variance is along the axis about which you're rotating. And what this does is it effectively increases, it's as if you have access to an ensemble that has a larger number of particles with an associated smaller amount of quantum projection noise. So that's the effect of the squeeze state on this overall stability. Another state, which is well known as a GHZ state, this is a state which is a superposition of all the particles in the ground state and the excited state, of course. And this is one which winds phase n times faster than the single particle frequency. So effectively what you're doing is gaining access to a clock that has an n-fold acceleration in its ticking rate. Finally, there have been a number of interesting proposals looking at variationally optimized clocks. These are clocks which both can encode an entangled state for doing sensing, but then also perform decoding on that state. This is a very nice protocol, which in general can give you enhancements in these quantities, but also the overall dynamic range of your sensor, which is typically an important consideration. So my group has done a couple, and one of the things that this usually is quantified in terms of this Wineland squeezing parameter C, which when less than 1 corresponds to a witness on an entangled state being used. And also means that your overall precision here is averaging down better than the unentangled case when C is equal to 1. Okay, so my group has explored these different kinds of states. So we had this paper in 2024 preparing cascaded GHZ states. I'm actually not going to talk about that today and rather talk about our work a bit before this. I'm preparing squeeze states based on an Ising model produced, the dynamics of an Ising model produced in the system. So the basic strategy that we take here is we combine this new clock platform based on tweezers with Rydberg interactions that you've heard about already in the workshop. And this gives us a platform for really having well-controlled entangled optical clocks. So the specific protocol that I'm going to describe follows from this proposal from 2014. The idea here is that the Ising interactions that are produced by the Rydberg Hamiltonian in the system look as follows. You have this long-range soft core potential where you have an interaction with saturates at short distances, and then after a characteristic distance RB actually falls off like 1/r⁶, as you expect for van der Waals interactions. If R, the distance between the particles, is much less than this RB, then you basically have a one-axis twisting model. What this means is that you have a rotation on the overall spin projection of the ensemble SZ by an amount that depends on your value of SZ. So this shears the distribution as shown here. So if I start with the coherent state, I had a rotation that depends on my value of SZ. So if you're further up, you rotate more. If you're further down, you rotate also more, but in the opposite direction. And towards the middle, you don't rotate. Once you have this sheared rotation, you can rotate it so that you have a distribution that looks like this, which is sensitive to translations along the y-axis or equivalently rotations about the z-axis. And so to do this, we prepare two arrays of atoms. Let's think of this as ensemble A and ensemble B. The interactions between the atoms in each ensemble are significant, but between the ensembles is insignificant. So we actually have two independent entangled ensembles here. We apply a pi over 2 pulse in the system. We apply this Rydberg dressing protocol that results in these interactions here. And then we inject this entangled state into a Ramsey sequence, which just measures these displacements in the ZY plane. And then at the end, we do a measurement that looks at the difference between the average value of SZ for ensemble A, so this top one here, relative to ensemble B. It looks like somehow my labels fell off this figure here. So we're just looking at the differential spin projection at the end, which in the end means that what we're actually measuring is the frequency difference between these two ensembles. We do this in order to reject common mode laser noise that can be a real nuisance in these experiments. Okay, so when we do this, what we see is if we plot the noise distribution as a function of the angle of the ellipse, so shown here, for certain angles, we see noise that is below the quantum projection noise that you'd expect for this size ensemble. And then at other angles, you see enhanced noise. This is just the anti-squeeze quadrature. The solid line here corresponds to our independent estimate of the quantum projection noise, and the squares correspond to control experiments where we don't apply the Rydberg dressing, and we just see that the data is near to the quantum projection noise as expected. One thing that's nice about these experiments is we can look at the microscopic correlations that are actually responsible for this variance reduction. So if you, for instance, are at this angle of 36 degrees where you have reduced variance, you see that you have negative correlations, which is exactly what you'd expect for reduced variance, right? If you're measuring something that has an average value of MZ that's 0 or SD that's 0, then you'd want to have anti-correlations such that they collapse in a way that reduces the outcome of them, reduces the probability of them collapsing in a correlated way. I understand why there's suddenly fireworks behind me. I don't know if everyone just saw that, but it's sort of interesting. Conversely, at the anti-squeeze quadrature, you have positive correlations, which is just again, the opposite of what I just described. It amplifies the noise and the wave function collapse. What you care about for the performance of the clock is not just the variance reduction, but also the residual contrast that you have in your interferometer, because this ultimately tells you about the authority with which you can measure a phase or an angle. The Wineland squeezing is the quantity that one typically refers to for this. This CW squared, you can see, drops at about 2 microseconds to a value of about 4 dB for these ensembles. So we have 4 dB of metrologically useful squeezing in these experiments. I want to highlight that at the time of this work, there were a number of exciting experiments generating squeezing and short-range interacting systems, which have an interesting set of many-body physics associated with them. So there was this paper from Antoine Brouweis's group looking at dipolar XY models, a paper from Monica Schleyer-Smith's group showing squeezing in ensembles of atoms in small dipole traps, and then also this work from the Roos group at Innsbruck where they showed squeezing in ion chains. One of the things that was distinct about our work was that we actually put this all together and put it in an operating clock to do a precision measurement. And then maybe I'll just go through this part a little bit fast. The upshot of this is that we could see that in the operating clock, we had about an enhancement in the overall performance of about 3.5 dB, and then an overall stability of 2.8 times 10 to the minus 15. If you look at the individual outcomes in the noise distribution for these two clocks, plotted in a parametric fashion, which is sort of how we're able to extract frequency differences, you can actually visually see the noise reduction associated with the squeeze states relative to the coherent spin states. Whoops. We can also scale this up to larger systems and still see this 2 dB of improvement and an overall improvement in the stability. The slight degradation in squeezing I'll explain in a moment. Yeah, by a moment, I mean now. So one of the things that we looked at was how this squeezing depends on atom number n. This solid line here corresponds to our expectation based on an analytic model that we don't expect to capture everything about the physics here, but should give us some guidance. And you can see that our data doesn't follow that at all. In fact, it's like basically saturated at about between -3 and -4 dB. Um, Part of this is due to a collective loss phenomenon that arises in these systems. This is, I don't know if anyone at the conference spoke about this, but this is this idea that when you're exciting atoms to Rydberg states, a black body photon can come along and excite the Rydberg atom to a different opposite parity Rydberg state, which then broadens the remaining atoms because there's a strong dipolar interaction between those atoms, such as basically what's shown here. And this strong dipolar interaction results in a runaway process, because then you can excite more and more atoms as the Rydberg spectrum gets broadened. One thing that we were able to show last year, or this past year, was that using a technique that was inspired by ideas from Monica Schleyer-Smith's group, we could use a combination of autoionization and stroboscopic Rydberg dressing to actually ionize these contaminant particles in the middle of the sequence to overall extend the effective coherence time with which we could explore the many-body physics of this system. So this in gray here is when we don't do this protocol, and in blue is when we do. So you can see the sort of increase in the overall timescales, which is quite nice for these squeezing experiments. The other thing that's important, and I'm getting towards the end here, is that there's overall, even the theory, which is the solid line, is worse than the one-axis twisting model and the Heisenberg limit. And this has to do with the fact that when you have a nearest neighbor Ising model, or a short range interacting Ising model, a pure Ising model, the correlations don't propagate. And so the idea here is that imagine I have two spins in the center here, spin A and spin B. If they point along the x direction to begin with, but are subject to an Ising interaction, then after they interact for some period of time, delta t, then their block vectors look like this in the xy plane of the block sphere, pointing along angles phi and minus phi, if I had an angle phi, a minus phi and phi here. And then you can ask the question, if I had, and this gives rise to correlations that look like non-zero zy correlations, but now imagine I had a third particle C here. The phase of particle B does not influence its Ising interaction with X, which is another way of saying that basically the Ising interaction is only sensitive to the Z projection and not your X or Y projection. And therefore your correlations do not propagate. In other words, you don't have a correlator between A and C at the end. So you have no real effective light cone in these systems. And this is a nice picture that Monica actually told me about for thinking about this. And this is also seen in our data. Basically, these correlation functions that we observe are very close to those that we measure for the actual size of the interactions over the system. And so the way to get around this is to add a transverse field. And effectively what this does is it converts the coherence, your projection in the XY plane, into an inversion in the Z projection. And then the Ising interactions can propagate that information and allow you to actually have an effective light cone. So there was a nice paper, actually this ion paper from the Roos group explored exactly this protocol, which was first proposed in this paper from a collaboration between myself and Anna Maria Ray at JILA. And then I'll sort of skip over presenting that point. Another idea is to actually stroboscopically, in sort of an interleave fashion, apply a transverse field in these Rydberg dressing interactions, which can allow you to, in a digital way, propagate these correlations and therefore extend the amount of squeezing that you have in the system to be more scalable, that is improving with the size of the system. Okay, with that, let me conclude. I guess I'll say this is actually exactly what we're working on right now. So the work that I just described was, the first part was led by Aaron Young, with key contributions from Matt Norcha, Nathan Shine, and Will Eckner, shown here. And then Will, Alec Zhao, Nelson Darkwa Pang, all contributed to the squeezing work, and Theo Lukinyala has been contributing to the more recent work with interacting systems. And so with that, let me conclude. Thank you.
Questions?
Yeah, thanks for the very nice talk. I guess maybe a technical question for the second part. It would seem that the experimentally measured squeezing become worse if you increase the system size. And from, like, without knowing too much detail about the theory part, it seems that the theory doesn't really capture this. So, like, is the idea that the collective loss is responsible for this, or like,
Yeah. So the primary thing that was limiting here, we believe, was the collective loss and actually also some like laser noise basically associated with the excitation laser. Um,
So,
yeah. And we
uh,
can see now a relative improvement between the two cases with and without this ionization protocol in the squeezing that we can achieve.
right. And can I just follow up to that, like
Yeah.
just to clarify, like experimentally, like is there like a regime where you see like squeezing kind of improve gradually, like as you increase the system size, or is this kind of in the ongoing work? Or maybe another way, so maybe as a serious, like what I'm really curious about is like, can you actually include those loss effects in the theory modeling and like kind of do
Yeah, that's an interesting
paramodeling?
question. Yeah, so we haven't done that just because we weren't. I mean, part of the challenge is knowing exactly how to model that collective loss. But going forward, I think that's something that one could definitely think about. Um, yeah,
So
and also there's I should say too, like in the poll paper, they look at uh, uh, how the squeezing improves with both dimension and atom number. And it's a little bit more subtle than this picture that I was giving here. It's like there's more to it than just what I was talking about.
right, okay, yeah, thanks.
Uh-huh.
Thanks for the very nice talk. I was wondering, maybe it's a bit naive and I don't quite know how clocks work, but is there sort of this trade-off that if you squeeze, then maybe you get better measurement precision, sort of at that point in time, but sort of overall your clock gets worse because you add some heating mechanisms?
Oh yeah, that's a great question. So in general, maybe the way I would say it is that as you add more entanglement to the system, if you have some or some local decoherence, so spontaneous emission or dephasing or deep whatever you want, then the decoherence of your many body state accelerates as a result of the entanglement in the system.
Yeah.
But importantly, if you're trying to measure a quantity that's fluctuating, then provided the time scales that you're trying to observe are short compared to your decoherence time, then the entangled states give you a win in bandwidth. So you don't ever get a win using entangled states in DC precision, but you do get a win in bandwidth, which is it's a somewhat subtle point, but that's sort of the way to think about it.
Okay, I think that makes sense. Like sort of you can use your clock for a lot of things, not just timekeeping, right? And sort of for these other applications, it could be.
Exactly, yeah. So like if you're trying to resolve, for instance, yeah, just to say like an out there example, like imagine you're trying to observe fast variations in the fine structure constant or something. Then you would choose a dark time that matched those fluctuations that you were trying to bound. And in particular, a dark time that you would want to be short compared to your single particle coherence time. Um, and that would give you an improved resolution and therefore bandwidth in sensing that quantity.
Perfect. Thanks so much.
Yeah.
Hi, Adam. Thank you for this nice talk. About the first part of your talk, I'm curious, like if you introduce spin degree of freedoms, what is our current understanding about how to get the entropy of the spin degree of freedom out in a strongly interacting system?
Oh, that's a good question. You mean like if you have like if you
Default.
wanted to pair like an SU2 route state,
Yeah,
like
right.
yeah. So I mean one thing that you can do, right, is this picture that I showed, um sorry, this is gonna be oops. Um oh, this picture is actually not helpful. I apologize. Okay. So imagine you prepare a band insulator, so two spins on every side, um of opposite, like two different spin states on each side, right? Then in the recent paper from the Griner group, what they did is they split each site by doubling the lattice periodicity. And in the presence of the exchange interaction, that couples you to the many-body ground state that you want to get to. Like you then have a spin one-half system. But the initial state is this band insulator, right, which you can produce.
Okay, so afterwards you kind of change the U if you want to go to.
Well, you change the lattice geometry.
I see, but okay, thanks. But if your initial, let's say I want to start a general Harvard model with kind of arbitrary ratio between U and T, right? But if I want to work in an intermediate region, which may be the hardest region to some extent, then it may not support band insulator.
Yeah, so I think that's a good question. The way that we've been thinking about this, this isn't something that we're doing now, but sort of we've thrown around ideas, is that basically if you can allow to have a reservoir with which you can exchange both charge and spin, then the whole idea of this protocol is that provided that reservoir looks metallic, it cools the central region. So if you initialize something that roughly looks like that, you might hope that you can actually cool the central region, but we haven't actually done calculations doing this. But I think it's an interesting idea.
Okay, thank you.
Mm-hmm.
Any more questions? I actually wanted to ask a question about the previous part on the atomic boson sampler. And the theory for boson sampling, of course, assumes a random unitary, but obviously experiments, we have to have some more structure. But it's very interesting in your setup, we have just bosons that presumably interact locally. So what can you say about how well your data approximates a more kind of standard boson sampling experiment? Or
Yeah, that's a great question. I meant to say something about that. So what we find is that, and this is in the paper. Unfortunately, I don't have a backup slide on this, but I can send it to you after. You can plot basically the distribution of single particle unitaries that are produced on the lattice as a function of time. And basically what you're tuning when you vary time, right, is the depth of the beam splitter network that you explore. So even though the beam splitter network itself is very local, you have like nearest neighbor connectivity, the resulting single particle unitary, as you allow that beam splitter network to get bigger and bigger, gets more and more diffuse. And so you end up with something that actually looks closer to the random unitaries that you would require for this. But of course, not perfectly exactly. Like I think if you really want to do this exactly right, you'd want to be able to, for instance, apply small potentials on top of the lattice to apply phase shifts also in the system.
I see. So the time scale that we evolved for is long enough that there is time for correlations to spread across the system.
Yeah, exactly. Yeah, right. I mean, it's just to be clear that not like particle-particle correlations. This is basically not interacting.
Right. Just
but like
modes.
but in the modes, exactly. Yeah, right. But I think an interesting question in this context is if you have a lattice, if you have dynamics like this, but you add interactions, which is exactly what we're doing in this next slide here, what statements can one make about the sampling complexity of that problem?
Thank you. Okay, so one last question.
Very quick question. So how do you prepare indistinguishable and distinguishable? Do you put different electronic state or different motional state?
No, actually what we do, so this was a very clever idea of my student, Aaron. So you just prepare the atoms. So imagine they're tunneling in 1D, okay? If I prepare all the atoms in the same row in which they're tunneling, then the label associated with the other dimension of the lattice, right? It's a 2D lattice, is the same, right? So that would be I could think of that as a 1D quantum walk, where I just count up the total number of particles in each column at the end of the experiment. Conversely, if I start with the 3 particles on different rows, then the row is a distinguishing label. And if I analyze the data in the same way, that's the physics of the distinguishable case, because the 2 lattice directions are separable.
I see. Thank you.
Mm-hmm.
Okay. Well, thank you so much, Adam. Let's thank him again.